Welcome to NucleCast, the official podcast of the ANWA Deterrence Center. Each week we bring you leading nuclear deterrence experts for a lively discussion on current topics. Our host is Dr. Adam Lowther, Director of Strategic Deterrence Programs at the National Strategic Research Institute. The views of the host and the guests are their own.
All right, and welcome into our latest episode of NucleCast. Of course, I am your host, Adam Lowther, and today we have Jim Howe. So for those of you that don't know Jim, he has a very unique background that is something I personally haven't had on the show before, so that I'm excited about that. So Jim is retired Coast Guard captain. He commanded cutters and spent some time in the Department of Homeland Security. And then he switched from the Coast Guard and DHS to uranium, which is, of course, one of the key reasons we have him on here. He worked in industry and worked on the nation's ability to have highly enriched uranium, which is, of course, why we have him on the show today, because as Jim's going to talk about, we have a lack of capability in this area of producing highly enriched uranium, which affects our nation's submarine force. And then, of course, thanks to the Russians, if we ever have a need to produce more of it. So we'll talk about these topics today. So, Jim, welcome to the show.
Glad to be here. Thank you.
So as you probably don't know this, but I was myself a Navy guy. I started my career as an 18-year-old bosun's mate. And so I, of course, have a love of the sea as well. But I wanted to ask you, as if you're trying to explain to people the difference between the Coast Guard and the Navy, how would you explain to somebody who asks you that question? What's the difference?
Well, the Coast Guard is the hard nucleus about which the Navy forms in time of war, is the way we put it. They tell us we're the people that can't be less than 6 foot tall in case we have to wade ashore. But the fact of the matter is, it's a great synergy between the two services. I actually spent 2 years working at a Navy command as a liaison officer, and learned they're kind of like the big corporate maritime service. I mean, they've got an amazing research and development system. They've got an amazing personnel system. The Coast Guard is a much smaller, so kind of it's the Walmart versus the mom and pop shop, but they can still get along. And you've got a terrific kind of overlap when it comes to the low end of conflict type of missions and the Coast Guard's capabilities to do things like maritime intercept operations, counter narcotics operations. I mean, if you're good at finding a drug smuggler who's trying to sneak 5 tons of cocaine in a semi-submersible up the Mexican coast, then you're going to be good at finding someone trying to sneak a WMD into the U.S. as well. So it's kind of an overlap of missions that's really effective. And the Navy is just terrific to work with. My last ship was a 270-foot cutter. We had a Navy weapons system, a 75 millimeter gun on the bow of the ship. All our command and control systems were Navy, so they would come down regularly and inspect the ship and make sure we were up to par. I really enjoyed working with them. So it's a great synergy. It's a great team for the nation.
Now, in your post-retirement, post-Coast Guard career, you've worked on the industry side of uranium enrichment. Could you? A lot of people probably don't think about this issue of the nation's uranium stockpile. Could you give us a little background and help us to understand why this is an important issue and why Americans should care about it?
Right. It's really essential that for everything related to the nuclear triad and to our nuclear deterrent, that we not have to depend on other nations, especially potentially hostile nations, to give us our feedstock or our supply chain. So if you go way back to the 1940s, of course, the U.S. invented the nuclear fuel supply chain. We were digging up uranium. We were buying it from overseas. We invented the whole enrichment process to build the bombs that ended World War II. And then, of course, during the Cold War, we and the Russians built a huge number of bombs that were necessary to keep the peace, which thankfully has withheld all these years. And so part of that is you have to have a steady supply of material that's enriched using U.S. technology. You can't be depending on foreign technologies because there's peaceful use restrictions to most enrichment technologies. And up until the 1990s, really, the U.S. kind of dominated this field. I mean, we were supplying, well over 90% of all enriched uranium to the Western and the free world, not behind the Soviet, the Soviet bloc and that sort of thing. And then, of course, you had a couple of private sector companies that are government owned emerge in Europe. You had a French company and you had a consortium company called Urenco, very good companies. And they got into the civil uranium enrichment market and really started to, take some market share. At the same time, the U.S. was going through a pretty interesting system of its own where we privatized our uranium enrichment. So it was part of the government up until the mid-90s. And in 1998, it was finally kind of spun off from the government as a private entity. So we're the company now known as Centrus is the only, basically privately owned uranium enrichment company in the world. Everyone else is owned in part or in whole by a government, which is interesting because when Centrus, which was then known as USEC, was spun off, it didn't really have a modern enrichment technology in place. It was using some really old 1950s era, what's called gaseous diffusion plants that were taking huge amounts of electricity. The last one that was running was down in Paducah, Kentucky. It was using $2 million worth of electricity a day, which is more than the city of Nashville, just to produce the enriched uranium. So when the rest of the world, the two European companies, the Russians, had all gone to centrifuge technology, which is a lot more, cost efficient, and we're using 5% as much electricity, their prices were much lower, and it really put this formerly government-owned entity, now known as USEC and later Centrus, in a really tough competitive position. To the point where by 2013, just due to the world dynamic, Centrus had to shut down the enrichment plant in Paducah, Kentucky. It just couldn't compete anymore in the world market. And so since 2013, there has not been a domestic uranium enrichment technology in operation. There is a technology that's the world's best. It's called the American centrifuge. It's something that Centrus has worked a lot on over the years. They've invested well over $2 billion in it. It's just not been commercialized yet because the market has been in tatters post-Fukushima. So right now, that technology is going to be used for a small demonstration for the production of high-assay, low-enriched uranium, which is stuff up to 20% enriched, which can be used in a lot of these advanced reactors and some of the things that DoD is working on with the Project Pele and other projects. So it's kind of an exciting time. I think the U.S. is on the cusp of getting back in the game big time in the uranium enrichment business on the world market. How that translates into the commercial market, I don't know. But for, national security applications and technical applications here in the States, I think we're going to be in a really good position in the next couple of years to take leadership in that respect.
Could you potentially offer some explanation as to what we use? Some folks may or may not be familiar with sort of enrichment levels for, nuclear power versus weapons versus, submarine power plants. Could you discuss that for us? Give us a little bit of the difference, and then maybe explain why having this capability is important, in particular for military purposes.
Certainly. So when you dig uranium ore out of the ground, it's less than 1% of the fissionable or fissile, isotope, which is uranium-235. That's a type of uranium that likes to break apart, and when it breaks apart, it releases a lot of energy. So to get it to a form where you can use it in a traditional light water reactor, and those are the 93 huge nuclear reactors we have all over the country right now, you have to enrich it to between 3 and 5% of uranium-235. So you go from less than 1% up to about 5% or 4%, and that's the enrichment process. Just a quick word on enrichment. It's really, really hard. Technically, it's very hard. It's very expensive. And that's probably a good thing because you don't want like 100 different countries enriching uranium. It took the U.S. a long time to kind of perfect it. It took the Europeans and the Russians a long time to perfect it. And that's a good thing because you don't want this to be an easy process. Right. But anyways, so anything above 5% is not enriched, is not typically used in commercial reactors. However, up to 20% will be used in some of these new advanced reactors technologies that are coming online, just because you have more bang for the buck. When you get above 20%, by law, you're now producing what's called highly enriched uranium. And bomb grade is in the 90% range. The highly enriched uranium we use to power our nuclear subs and nuclear powered aircraft carriers are in the 90% range. I'm sure the official number is sensitive, but it's way up there because you get so much power density of that level of enrichment. And the U.S. nuclear Navy obviously is the best nuclear program that's ever existed in the history of mankind. It's ultra safe, ultra professional, because they're using some very important, sophisticated technologies that you have to do it right. You don't want to have mistakes, and they do it perfectly right. They're the best in the world. And that's what you also find trickling down into the nuclear industry. First of all, it's populated by a lot of people that spent time in the Navy, which is a really good thing. But you have this great synergy also between the civil nuclear power industry in the U.S. and our defense needs. So why do you need enriched uranium? Well, one is every one of our nuclear weapons requires a substance called tritium that is used to kind of boost the yield of the weapon. So it's in every one of our nuclear weapons. But you have to produce a steady supply of tritium because it's got a half-life of only 12 years, 12.3 years. So to produce tritium, you have to do that in a reactor, usually. There's other ways to do it, but the easiest is in a reactor. And that reactor has to be fueled exclusively by domestically produced uranium that can't be from a foreign technology, that sort of thing. So the really excellent company out in New Mexico, Urenco, that's enriching uranium for the civil commercial fleet, their material cannot be used to produce tritium for our stockpile. Right now, the National Nuclear Security Administration has enough, kind of excess uranium to keep that process going for about another 15 or 20 years. So you don't have to have an enrichment capacity right away, but we think it's important to get enrichment capacity up pretty quickly because you've got a lot of other emerging needs for enriched uranium above 5% that currently can't be met unless you buy it from Russia, and no one wants to buy it from Russia. Some of those needs are, for example, space nuclear thermal propulsion. Both NASA and DoD are looking at building nuclear-powered rockets. This is something we've been doing all the way back to the 1950s. We've never successfully fielded one yet. But those are going to use materials enriched up to about 20%, this high-assay, low-enriched uranium, which you cannot get on the world market right now, except, like I said, from Russia. So you want that to be a domestically sourced thing, especially if it's for a military application. And then you've got Project Pele, which is a mobile microreactor that is going to be built by BWXT out at the Idaho National Lab. It's going to be a demonstration in the next couple of years. They're going to be using enriched uranium up to 20% as well. So for the one demonstration, they've got some in the stockpile they can use. But should DoD choose to employ a number of mobile microreactors or fixed site reactors, which is another demo going on up at Eielson Air Force Base, they're going to need a supply, and you certainly don't want it coming from overseas. So that's a real compelling reason why we need to reinvigorate this nuclear supply chain, get it in place to make sure that the feedstock is there for these advanced nuclear technologies.
And do we have sufficient uranium ore that is domestically mined to then be processed, or do we have to buy from overseas?
Yeah, there's plenty of ore that is available in the U.S. The only question is, are there the companies that, are up and running to do it? I mean, the U.S. domestic mining industry, first, they're wonderful people, hardworking. We have the cleanest uranium mining in the world. We don't do it most of the time, virtually any time, by actually digging into the ground. You do it through what's called in situ, where you stick a pipe in, you pump in a certain fluid, you extract the fluid, and then take the uranium out of that. So it's a very clean process, virtually no environmental impact whatsoever. Very easy to clean up your facility once you're done mining a certain locale. But because of the world market, most of those companies are kind of just in a holding pattern, not really producing right now. The price of uranium has been very, very low over the last 10 or so years, just because the market's been flooded by overseas competitors. Most uranium used in the commercial industry right now comes from Kazakhstan, who can mine it a lot cheaper than you can do in a Western country. And then you've got great deposits of uranium up in Canada. We buy a lot from there, Australia as well, two very friendly nations to us. So there's plenty of supply in the U.S. It's just that our domestic industry has not been positioned to kind of extract it just because of the economics of the situation. I think that's going to change. There's programs within the Department of Energy right now to kind of help catalyze the domestic mining industry. You also need a domestic conversion industry, which is a step between mining and enrichment. The one conversion facility we have in the U.S. has been shuttered the last 4 or 5 years. They're supposed to come back online next year, which is a really good development. So again, the industry is starting to rebound, from soup to nuts. It's just that we're not there yet. We need the government to keep kind of pressing forward on a lot of these innovative programs.
This episode of NucleCast is brought to you by the ANWA Deterrence Center, whose mission is to educate Americans about the nuclear enterprise and strategic deterrence. So what do you see as the most pressing needs for uranium production and enrichment? We've talked about weapons, we've talked about tritium requirements, the warheads themselves have it, but we have a lot of decommissioned warheads, so we can draw from there. We've also talked about, commercial use, which this is low enriched. You've mentioned this up to 20% for some of these newer reactors, and then up to 90% for Navy requirements. And then you even mentioned space and nuclear fueled, which that's an interesting one. Could you perhaps, tell us a little bit about that and where you think we're going there? And then also, where do you see the most pressing needs sort of in the short term?
Yeah, the pressing need is to kind of have the government help jumpstart this industry, both the fuel supply chain as well as the advanced reactor industry. And that's happening. It's the question of how fast it happens and how effectively it happens. The Department of Energy, Department of Defense have some incredibly good programs happening right now. Department of Energy is actually helping 10 different advanced reactor technologies get on their feet. 2 of those reactors are actually going to be deploying demonstration reactors by the end of this decade, maybe a couple of years earlier. And then, of course, you got Project Pele for DOD under the Strategic Capabilities Office, which is going to have that microreactor up and running out at Idaho National Lab in the next couple of years.
Could you maybe explain a little bit more about that for us and what's the purpose of it?
Sure. So the question is, when you have expeditionary forces around the world somewhere, whether it's for combat operations, whether it's for disaster relief, whatever, and you need a lot of electricity, and if you look at it as our capabilities in the military realm need more and more electricity as we electrify a lot of our combat vehicles and laser systems, all that, you're going to need more electricity. So right now you get it through diesel generators mostly. Well, think of that. How many diesel generators do you need in at a forward operating base versus one compact, small micro reactor that could come in? You could set it up in just a couple of days and just power your little local grid there as long as you need it. Or if, a friendly nation or island gets hit by a very bad hurricane or an earthquake and you need power and you want to hook something into the grid and you fly in a micro reactor and just hook it into the grid, boy, there you go. You've got everything kind of, right there at your fingertips. So it's a really compelling technology. Now, look, whether the policymakers will decide to move forward with it is a question. I don't know. You've also got, I think, quite frankly, it might be even more attractive is the idea of using microreactors for fixed site DoD installations that currently live off the electric grid. So if you have a power outage near a large DoD installation, they probably have a bunch of backup diesel generators, to keep the essential functions going. But what if that large DoD facility was run by just one reactor that, is going to just run continuously, steady state, baseload power, never has a problem with the weather, that sort of thing. You don't have to worry about relying on the grid. I think that's a very compelling argument to make. It's environmentally clean. You've got no carbon emissions whatsoever. And so why not pursue that? Well, the Air Force is pursuing that. They're going to have a microreactor up and running at Eielson Air Force Base in Alaska in the next 5 or 6 years. And they've just recently came out with their request for proposals for that. So this is a really unique and kind of a pivotal time for the industry, because if DoD can start, buying some of these microreactors, it will jumpstart the commercial industry, and that will allow these companies that are investing a lot of their own dollars in this, to see a profit horizon where they can start building a lot of reactors, sell them to places like, for example, you go to northern Canada where there's a lot of mining communities. There's a lot of places that right now depend on large amounts of diesel fuel being shipped across the tundra. If you can avoid all that through one small microreactor, what about high temperature applications such as production of hydrogen or the production of chemicals, where right now you're burning a lot of diesel fuel or other hydrocarbons to produce those? That's a really kind of target rich environment for the commercial sector. But until they get jump started, it's going to be hard for them to, get the seed funding, all that sort of thing. So it's a very synergistic type of approach that I think as DoD moves forward with their programs, is going to really help the commercial people and vice versa.
As you look specifically at sort of the challenges for DoD in the, this area of uranium processing and enrichment, and you sort of project out in the strategic environment in which we find ourselves now, which is certainly not where we thought we'd be 10 years ago. What do you see as the biggest, potential pitfalls or areas where we could see a black swan that is, subsequent to that black swan, we are, having a moment where we're like, geez, we wish we would have been prepared for this?
Yeah, I think in general, what needs to happen now is a continuation of what's already started. Both DoD and Department of Energy are really moving forward fairly quickly on getting some of these new nuclear technologies to market or to, be tested for DoD applications. So what we can't do is kind of stop that forward progress. We need to just move ahead. Let's get these demonstrations done. I think once you demonstrate and show the effectiveness of these reactor technologies, is going to really be a game changer. If you really look in the big energy market, how do you have a clean energy economy? Well, everyone talks about things like solar power and fission and all that. Well, fission is, however many years away, probably at least 10, probably 20 when you talk about commercialization. Solar power is great, but it's got some limitations, such as the sun is only up half the time. So now you have to have a lot of battery storage. Nuclear is amazing in that it's base load power 24/7. It's very safe. A lot of these advanced reactor designs are meltdown proof. You literally couldn't melt them down. There's one based on a technology called the EBR-2, which was something that was demonstrated out in Idaho. The government, Department of Energy, ran this reactor for almost 30 years, and they tried to damage the reactor and make it melt down. They couldn't do it just because of the natural physics of the way it's designed. It shuts itself down without any problem. So you've got these great technologies that are currently not deployed commercially, that once they get deployed, I think are going to be well accepted by society. They are things where you don't have to have as much societal impact of 10-mile buffer zones around a reactor because of safety concerns. You can literally have fence line type safety concerns where, again, you can't really do anything to harm the environment or the people around you. So So these are exciting times. It's just, let's keep the momentum going. And as the Department of Energy, the Department of Defense, they demonstrate these technologies, I think the commercial market's going to gobble them right up, and we're going to really lead the world in selling advanced reactors around the globe.
If you were to leave, our listeners with a couple of takeaways, because this is the topic, I'll be honest with you, we've never had a discussion about uranium enrichment. We've talked about pit manufacturing for weapons. We've talked about these pretty standard topics. And so to have you on to the show is great because it sort of takes us in a direction we've really never gone. And so as we think about the end of the show and you want to leave the audience with some key takeaways, what would be those things that you think they really need to know and sort of understand?
Well, one is that anything dealing with nuclear is expensive. And when you deal with the nuclear supply chain, the fuel supply chain, it's very expensive. Uranium enrichment to build a plant is in the billions of dollars, not the tens of millions, not the hundreds of millions. At the same time, I think we're seeing some successes that have built upon themselves. So let me go back. You had asked earlier about space. We have been working on space nuclear rocket propulsion since 1955. And from 55 to 72, we had a program called Project Rover, where we actually built and demonstrated in the Nevada desert 22 separate reactors that were going to be used as incrementally as the reactor for a space nuclear rocket engine. The program was shut down in 72. Another program came along in the 80s and 90s called Timberwind. They were going to use a nuclear rocket for part of the space or the Strategic Defense Initiative. That went away. And then in the early 2000s, there was a project called Prometheus at NASA. They're going to use nuclear electric propulsion to send a large robotic spacecraft to explore the Jupiter's icy moons. None of those programs was ever fielded. It never quite got to the final point. But the point I'm trying to make is that there's been so many advances in things like advanced manufacturing, additive manufacturing, in computing power, where you're able to take this work that's already been done, this huge body of technical work, and you're able to apply it to new technologies much, much cheaper. So here's the example. In the 1980s and 90s, there was a space reactor concept called SP100. Department of Defense, Department of Energy, and NASA all teamed up together, and they were going to build a space reactor of about the 100 kilowatt range, and they spent over $1 billion in linear dollars and never really got an operational prototype, never sent anything into space. Just a couple of years ago, NNSA plus NASA plus DOE plus several of the labs got together and did a smaller version of that called Krusty, which they actually got this small reactor up and running out in Nevada for $20 million. Now, how were they able to do that? Because they took all the old work and they kind of built on it. So they didn't have to replicate things that had already been done. So I think the same is true for things like these advanced reactors, where you're going to be able to build a lot of them much more cheaply once you start getting unit production, build them in a factory and not on site, that sort of thing. I think the same thing is true for the nuclear rocket technologies that DARPA and NASA are looking at. I think you're going to be doing it a lot less expensive than you have in the past, just because technologically we've come so far in material science, in computing power, in the types of manufacturing we can do, where I think that it's a really golden era we're about to enter into if we keep the momentum going. So that's the real takeaway, is keep the momentum going.
All right. Well, thanks for, I found that interesting just because it's a topic that I have to admit I didn't know a lot about. And I think many of our listeners will also admit that it's not a topic they know a ton about. So thanks for coming on the show, Jim, and offering us some very interesting thoughts on uranium enrichment, on the future of nuclear energy. I didn't realize how safe and sort of compact some of these. I've heard about the new systems, but I don't think I realized just where we were technologically with them. So thanks for bringing that to the show.
Yep, you're welcome. It's a pleasure to be here.
All right. And listeners, we look forward to to being with you again. We have a lot of folks that we're going to be bringing onto the show in the weeks ahead. So we'll look forward to having you listen to the next show. And thanks again, Jim. That was a very enlightening show.
Thank you.
Well, so we just had a show with Jim Howe, and we talked about uranium enrichment. It's a topic I don't really think about that much. And so it was interesting. And what I found particularly interesting, and Jim and I talked after the show, was the number of programs where we're looking at using nuclear power in space. And that we've been doing this since 1955. And we've had, programs throughout, the history, and NASA's been a key player, the DoD, the Department of Energy. And so this idea that we need enriched uranium for all of these programs and for the new reactors that are coming online, for me at least, that was pretty interesting because it's just not something I think about a lot. And sort of discussing the safety issues, because we all think about Fukushima and we think about, the accident in the Ukraine and, the 1980s with the war in particular going on right now, where they're fighting around these nuclear power plants and, could Chernobyl happen again? Things of that nature. You often wonder, is nuclear power really safe? But Jim sort of walked me through some of the key designs. We talked before and after. And so that was interesting. So, that's kind of my thoughts on the show today. So hope you'll enjoy it.